Hello everyone, I'm Giuseppe Lovisi and I will illustrate the main results obtained with the collaboration of Professor Luciano, Rosa, Penna and Arturo Pascuzzo in the work entitled A Stress-Driven Model Incorporating Surface Energy Effects for the Bending Analysis of Function-Graded Nanobeams with Discontinuities. The presentation will follow the following points: introduction, state of art, material, scope and novelty, results and discussion, and finally conclusions. In recent decades, there are hundreds of applications of nanomaterials in various sectors, especially in the field of NEMS. Nanotechnology is science, engineering, and technology at the nanoscale, and indicates the set of techniques and methods aimed at creating a system in which at least one dimension is of the order of nanometers. As it is well known, for the study of the static and dynamic response of the nanobeams, it is necessary to use a non-local elasticity model. Hence, the classical Cauchy local continuous model in which the stress at a point depends only on the strain at the point cannot be used. In 2017, Roman and Barretta have been introduced the integral stress-driven model, which appeared well posed from a mathematical point of view and provide a coherent approach for the study of nanostructures. The integral form is equivalent to the differential form if and only if the two pairs of conservative boundary conditions are satisfied at the nanobeam ends. The term Lc indicates the characteristic length and is a function of non-local parameter, which allow you to capture the small-scale effects, while M and K indicate the bending curvature and bending moment respectively. As the size of a structure decreases, the surface area to volume ratio increases, and the surface area region cannot be neglected. For nanometric side structures, the energy stored in the surface, also called free surface energy, is significant and leads to the formation of residual surface tensions and elastic properties different from those of the bulk. Consequently, classical continuum theories, in which non-local and surface energy effects are usually neglected, need to be modified to incorporate small-scale and surface effects. The surface property is dominant at the small scale. One of the first mathematical theories incorporating surface stress was proposed by Gurtin and Murdoch. The surface of the nanobeam is modeled as a zero-thickness membrane perfectly bonded to the underlying material, and no slipping between surface and the bulk material is admitted. Moreover, bulk continuum and surface layer are characterized by different stress states. A uniaxial stress state for the bulk, but unlike classical Bernoulli-Euler beam theory, the component of the bulk stress in the transverse direction, which describe the surface layer and the bulk interaction, is not negligible due to surface effects, and is assumed to vary cubically along the Fg nanobeam thickness according to the following equation. While for the surface layer, the two relevant conservative relation is formulated as follows, where Es is the Euler-Young modulus for the surface layer, and tau S is the residual surface stress. Function-graded materials have become of great interest in numerous research fields, as shown in this slide. For the study of these materials, it is necessary to use a micromechanical model, such as the Dvorak model, where N indicates the gradient index of the material, while Pc and Pm are the generic physical or mechanical properties of the material listed in the table. In this work, ceramic and metal are coupled. The aim of this work was to couple stress-driven local model with the theory of Gurtin and Murdoch for a function-graded material in presence of a crack or load discontinuity. Combining the above theories, the governing equation incorporating the effect of surface energy in terms of transverse displacement of each part of an inflected Fg nanobeam can be enumerated as follows, where Ai is the equivalent bending stiffness to take into account the surface effects, while Ts is defined as follows. Let us assume that the Fg nanobeam has an edge crack located at a distance d from the left end, which divide the nanobeam into two parts, B1 and B2, subject to distributed loads. To take into account the effect of the crack, we use the method proposed by many authors, and the crack can be modeled as an elastic spring at the cross-section between the two parts B1 and B2, whose flexibility constants are denoted as Kmm, Knn, Kmn, and finally Knm. Due to the presence of an edge crack, we can evaluate an increment of the strain energy with respect to intact nanobeam. In this work, the crossover flexibility constant Kmn and Knm are assumed to be zero. Moreover, no longitudinal displacement is considered. Only the bending problem is investigated, and hence the increment of the strain energy related to Kmm can be expressed by the following relation. And consequently, the following relative boundary conditions at the crack position must be considered, where K indicates the crack severity. Thus, we have two equations for each part of the nanobeam. The equation in red for the left of the discontinuity, and the equation in green for the right of the discontinuity. The above two equations, which present 12 unknown constants, must be solved with the specified boundary conditions. 4 boundary conditions, 4 standard boundary conditions, 4 compatibility boundary conditions at discontinuity, 2 constitutive boundary conditions, and 2 constitutive continuity boundary conditions. So we have 4 standard boundary conditions, and in red are highlighted the terms which take into account the surface effects. We have 4 compatible boundary conditions at discontinuity, in particular continuity of the vertical displacement, jump in bending slope, in which we can take into account the crack severity, continuity of the bending moment, and continuity of the shear force. The constitutive continuity are introduced by Romani and Barretta in 2017 and constitutive continuity boundary conditions. In particular, the constitutive continuity boundary condition introduced by Caporale et al. In 2020 are here modified to take into account the surface effects. For reason of timing, now I show you only the main results obtained for a clamped pinned functional nanobeam in the presence of discontinuously distributed load and the crack severity. In this slide, we show the dimensionless deflection for different value of crack severity for both stress-driven model with and without surface effects. As it is easy to see, the stress-driven model that takes into account surface effects always gives lower value than the stress-driven model without surface effects. By comparing the two figures, as the non-local parameter increase, both models provide a stiffening response. Also, as the crack severity increases, the deflection increases. In this slide, we show the results in terms of dimensionless deflection for both models and for different function-graded materials. In this case, it was set on a local parameter equal 0.2 and the crack severity equal 0.065. In particular, as can be seen, the dimensionless deflection always increases as the gradient index of the material increases. In view of the numerical results obtained in the present study, the following conclusions may be formulated. The deflection increases always by increasing the material gradient index. An increase in the value of the non-local parameter always leads to a decrease in the deflection for both models. The deflection always increases as the crack severity increases. And finally, the surface energy effects cannot be neglected, and stress-driven model with the surface effects gives lower value of maximum dimensionless deflection than the stress-driven model without surface effects. Thanks for your attention, and in this slide I reported my mail for any question or clarifications. Thank you.